All right, so today we finally get to be introduced to integration, which of course is the reverse of differentiation. And we're going to learn what this is all about, how it works, how it's defined. And we'll see as we go along that integration is in many ways more complicated than differentiation, but it's awfully, awfully important. So we'll start by introducing the idea with the following graph that when we take an integral, what are we actually doing but finding the area under a curve between two endpoints. So here, for example, you can see that whatever this function is, if we take the integral, and again, I think I mentioned this before, this symbol is used to represent an integral. And as we'll see, it actually represents an infinite sum. What it represents the sum of is you have to visualize that in this shaded region, we have an infinite number of rectangles that we're adding up. So, but we'll get to that in a bit. So here, if you notice, it's written in such a way that we have the integral sign. We also have the two endpoints here, a and b. Okay, so this is a closed interval from a to b. A and b are both included. And so the a and the b are written on the integral sign to remind us that we're integrating over the interval from a to b. Okay, so we apply whatever rules are appropriate. We come up with a function, and then we can make the substitutions of a and b, and we'll come up with our solution. So what we're actually doing, like I said, is determining the area under this curve between a and b. So, but the process that will follow is basically the reverse of what we would do if we were taking a derivative. Okay. By the way, there's two different types of derivatives. Integrals. This one is called an indefinite integral because it is defined over the entire real number line. And this one is called a definite integral because it is only defined over that interval from a to b. Okay, so they both require us to use the same techniques. It's just that when we have a definite interval, we have to then substitute the values of a and b to come up with a specific result. Okay, so now what we're going to do is introduce what exactly is happening with an integral. You're basically using geometry here. You're actually taking a series of rectangles and well, we'll see in a couple of minutes, but you're creating a series of rectangles underneath that curve. And what we're allowing to happen here is that the widths of the rectangles are actually being reduced. And in fact, in the limit, as the widths of those rectangles approach zero, then the sum of all those rectangles is the integral that we're looking for. Now, by the way, just in case you've forgotten how this works, we're going to be using this summation operator. It is the Greek letter sigma, and we use it to represent the fact that we're adding a group of numbers together like this. All right, so what does this mean? So first, this is the Greek letter, specifically uppercase sigma. So we see something like that. We have here an index, which means we have I equals 1, 2, 3, 4, all the way up to n, whatever that happens to be. And then x is indexed. X is some variable that's indexed by I. So what you're basically being told to do here is this. Okay, so that means that we have n of these x terms and we add them up. It's really that simple. Now all right, let's just do a couple of simple examples, but we can actually do a lot of very complicated calculations with the summation operator. For example, here, this is a very simple case. What if we discover that in the first 5 days in January, the temperatures observed in Minnesota are, and you can see here, they're very cold, 2 degrees, -1, 3, 5, and 1. So the summation operator would tell us that the sum of these first five temperatures is 10. Okay, so in other words, what you would have here is that n is 5, and then this is our x1, this is x2, this is x3, x4, and x5. We can also have summation on functions of x, for example, using the same data. What if we were more interested in the sum of the squared temperatures for some bizarre reason? What we could do then is, as you can see here, we would square each term separately and then add them up, and that would leave us with 40. Okay, so the key here is that you're squaring the numbers and then you're adding them. The way it's written, you're adding up the sum of the squared x's. On the other hand, if you're squaring the sum of the x's, which is very different, that means you're adding them up first and then you're squaring the result. And you can see here, we've added up the x's. And whatever that sum is, which we remember is 10, is then squared and we get 100. So you can see that these two did not give us the same results. And in fact, they usually do not. So this concept is going to be very helpful again in Calc 2 and 3. So we're willing to spend some time reviewing this if you've forgotten how this works. Now, here's something that you run into sometimes. What if instead of the previous two examples, what we're being told to do is for each x, we subtract this k constant and square the difference before we add them up. Okay, so this is what it would look like. And you run into this a lot in statistics, by the way. If you've ever had a stats class, you'll know that we use these all the time. For example, the variance is defined with what you're seeing here divided by the sample size minus 1 if it's a sample variance. So let's try an example. So again, using the same x's, we have x1 minus this constant 3, x2 minus this constant 3, all the way out to x5. And of course, at each step, we're going to square the differences. And then we'll add them up. Okay, so you can see if you go through the all the steps, you'll end up with 25. All right, so those are just some simple examples, but we're going to extend this a little bit by showing some basic algebraic properties for the summation operator. For example, what if we're adding up not x, which is a variable, but c, which is a constant? Well, what's happening here is that we're adding up c n times. Okay, so let's say, for example, if n is 5 and c is 2, what you're seeing here is 5 times, and that gives us 10, which is, of course, the product of n times c, or 5 times 2. Okay, so adding up a constant means you're just multiplying. Okay, all right, there you go. Now, by the way, algebraically, then we can factor the c out of this expression because it gives us the same result. Okay, these two mean the same thing. And in fact, often we find that it's easier to simplify whatever we're doing by moving constants outside. So for like this one, if I'm looking for double the temperature every day, the sum of double the temperatures, then I could have rewritten it as 2xi, and that just tells me that for each xi, I'm just doubling and then adding them up. And of course, I'll end up with 20 because remember before the sum was 10. It stands to reason that it would have to be 20. All right. The sum of two individual sums can be written in the following way. So in other words, we can break it up into two parts if there's some reason for it. Or alternatively, we can just take these two individual sums and combine them as you see here. So the important thing is that we must have the same index and the same number of terms. Otherwise, this doesn't work. And of course, if that's true for addition, it must be true for subtraction down here, you can see. And oh, now what's happening here is we're breaking up the index. Here, the index is going from I to N. So here what we did was we broke it up into I goes from 1 to M, and then from M plus 1 up to N. Sometimes this can come in handy. In fact, you'll see why we're explaining this now, because it'll come in handy when we introduce the definition of integration. What's going to happen is sometimes the function stays above the axis, sometimes it falls below. We have to have the ability to split up a sum into individual parts to illustrate the properties within these two ranges. In other words, it may be that, for example, this gives us a positive result and this one is negative. We want to be able to tell where the each of these is coming from. All right. Now, by the way, what you're about to see, these are formulas that could come in handy when you're looking at topics like sequences and series. Nobody says you have to memorize these, but once in a while, you might find that it comes in handy. Let's say, for example, here, if I wanted to add up, the numbers 1 through 10. I say, I don't feel like adding up all 10 numbers. Well, because n is 10. And I tells me that I'm adding up these 10 numbers. What this is telling me is that I don't have to add them up. All I have to do is note that what I've got here is 10 times 11 over 2, which is 55. If you go ahead and add them up yourself, you'll see that it is, in fact, 55. So sometimes these formulas can come in very, very handy. Like here, okay, here's 1 through 5, and you can see that we can confirm this. N is 5 in this case, which means n plus 1 is, of course, 6, which means that we end up with 30 over 2, which is 15. Oh, now what about this one? What if we're squaring adding up the squared i's? In other words, instead of 1 plus 2 plus 3 up to 10, which we just saw equals 55, what we're doing is adding up 1 squared plus 2 squared plus 3 squared. Okay, well, according to this formula, there is a way we can do this directly without actually squaring them and then adding them up. And you can see this is going to save us some time, because all we need is 10, 10 plus 1, 2 times 10 plus 1, over 6, which is the same thing as 10 times 11, 21. And so, what's that? All right, 10 times 11 times 21 divided by 6 is 385. And you can go back with your calculator and confirm that this is correct. So for these, for the first 5, that is, if you use the formula, you'll see that it should be 5 times 6 times 11 over 6, 55. All right. Now, by the way, most calculus books, I'm not sure if this one has one, have a table of all of these different summation formulas. There are quite a few of them, as a matter of fact, and you never know when they might come in handy. This is just sort of the tip of the iceberg. But you probably there's a table in there somewhere, and it'll show you a large number of the most important ones. Like, for example, we may end up with, there you go, I cubed. All right. And by the way, it turns out that a lot of the trig functions can be expressed this way. It's kind of interesting how they can be broken down into these sums, but that's a topic for another day. All right, let's confirm this one. The sum of the first 5 cube numbers is going to be, so n is 5, n plus 1 is 6. So this will give me 25 times 36 over 4, 225. All right. Now look at this one. We're going to run, oh my God, that's a huge one. 1 through 200. But what we want to do is not add up those individual numbers, but we need to subtract 3 from each one. So, wow, this is combining multiple concepts that we've already seen. So here's one thing we can do. There's no formula in any book for I minus 3 squared. It's too specific. But if you see what we've done here is we've squared I minus 3. And you can use any technique you want. You can use FOIL if you want, and you'll end up with I squared minus 6i plus 9. And then broke it up into these individual terms. So you can see now, suddenly this ability to break up the sum into individual terms is going to be very helpful because we should be able to find formulas for these. And by the way, what we're going to do here is one more step. This one, we're going to factor out that 6. And of course, this last one is a constant. So we already know the formulas for I squared, sum of the I squares rather, the sum of the i's and the sum of a constant. And so they should look very familiar. So we start by solving for the sum of the first 200 I squared terms using this formula we saw a little while ago. For the I, now remember the 6, this is actually minus 6 because we moved it outside and we're subtracting it. And so we plug it into this formula. Minus 120,600. And then the constant, we know how that works. It's just 9 times n, which means 9 times 200, which is 1,800. And there you go. So I think you'll agree that that was faster than actually going through all 200 of these terms and subtracting 3, squaring, and then adding them up. That would take a very long time. But by breaking it up like this and taking advantage of these formulas, we can speed things up quite considerably. Oh my God, now we're really getting out of hand here. Not really. You've got I cubed minus I squared from I equals 1 to 6. We know those formulas. So let's figure them out. So here's I squared. You plug in n is 6, of course. And here you get 91 for I cubed. Using that formula, we get 441, again, because n equals 6. And so the difference between them is what we need, which is 350. Okay, so now we're pretty comfortable with this summation notation and some of the algebraic operations we can perform on it, as well as some standard formulas. Good, okay. And again, like I said, this will show up again in Calc 2 and in Calc 3. This is one of those topics that will be useful many, many times. Okay. Now, we're ready to look at approximating an area under a curve. Okay, so this is where we're justifying how integration works and think of it in terms of a sum of rectangles. So we're assuming, first of all, that the function is continuous everywhere. We're going to start only by restricting ourselves to the non-negative functions, meaning that they're everywhere above the horizontal axis. We'll relax that assumption later on. We're going to only consider a closed interval a to b. So here it is. We don't know what this function is. Capital A is the area under that curve. And this is what we would get if we integrate f of x from a to b. Okay. The dx we always put there in the under the integral. You'll see why in a second. And so this is how we write a definite integral. And we have the result a. But why? Well, here's what we're going to do. We're going to take this and basically break it up into a series of intervals, subintervals actually, indexed by I. So in other words, we're going to have a series of xi's. Now, the way, like here, let me just show you quickly this graph. We're going to start here with x0, x1, x2, all the way up to xn. And so, for example, we have a single rectangle right here. If there's more room, I'd like to write it in here. This is x1. And then right next to it is the interval from x1 to x2. Okay. Actually, let me see if I can find some more room here. Say here's our function. Here's the horizontal axis. Okay, so I didn't draw that one as well as I would have liked to. What's the important detail here is that within each of these rectangles, the interval has the two x's, x01, x12, et cetera, within each, for each rectangle. The interval that we're looking at is written as x0 to x1. Actually, I'm sorry. We're going to write this as xi minus 1, xi. And so we're going to run from I equals 1 to n. Let me just copy this here. So in other words, because of the way it's written here, I goes from 1 to n, which means in the first interval, that index is I minus 1, which means it's 0. That's why we start with x0. And then the one to the right of it is going to be our x1. And so we'll go all the way out to the end. The last rectangle, this one, goes between xn minus 1 up to xn. Now, this is what I want to point out. It's hard to tell with such a small diagram, but if you look at it carefully, the height of the rectangle on the left endpoint always exactly touches the curve. Okay. The right endpoint doesn't necessarily touch the curve. In fact, in these cases we're seeing, in each case on the right endpoint, the rectangle doesn't touch the curve. Okay. So, but we're making sure that the left endpoint touches the curve. So in other words, the rectangle starts exactly at the curve. Then we draw a horizontal line across to the right endpoint, and then we connect them, and that becomes our rectangle. So you can see we're not capturing the area under that curve perfectly. We're missing some areas here. Okay, we're only getting an approximately correct area when we do it this way. So if I had another one, and if the curve was facing down, it would be the other way around. Let me just try to throw that in here for you. Now, let's say this is our function. So we start with x0. There's x1. See, now it's the opposite case. At the left endpoint, the rectangle exactly touches the curve. But now look at what's happening with the right endpoints. Those rectangles are above the curve. So we're still getting an approximation. This approximation is too large. This approximation is too small. Uh-huh. Now, by the way, what we're doing here is called left endpoint approximation. When we make sure that the rectangle is touching the curve at the left endpoint, we call that left endpoint approximation. And we'll see in a bit how this would work with right endpoint approximation. But let's focus on this one. Now, each of these rectangles has an area. And of course, if you recall, the height of an area of a rectangle is the height times the width. Now, we're going to define delta x to be the difference between each of these points. In other words, the distance between all of these is called delta x. Right? They have to be the same. Otherwise, we have chaos, right? Each of these rectangles is assumed to have the same width. It's the heights that are different. Okay. Now, the heights are going to represent the function evaluated at the left endpoint. So this is, in other words, think of this as rectangle number 1, rectangle 2, etc. Rectangle in, and this is the width, and this is the height. In other words, it's touching the function at that x, the left endpoint, so therefore that is its height. Okay, so I didn't actually draw that in here, but this first one, the height would be f of x0. And this next one, it would be f of x1, etc., etc. Because we're evaluating the function there at the left endpoint, and the height matches that exactly. Not the right endpoint, we know that, but the left endpoint has a height of f of x0. Anyway, that being the case, we can easily calculate the approximate area. If you notice, what we've got here is, for each of these terms, we have the approximate area of that, actually, I should say the exact area of that rectangle. And then we just add them up. So if you notice, the area here is listed as being approximately equal to we're going to call it ln. The book ln just means the combined area of these rectangles. And well, we can write it more formally using our new friend, the summation operator. And if you notice, the way it's written, the index goes from I equals 1 to n. So we start with the left end point. So that's why it's written as I minus 1, so that the 0 comes from the fact that I is 1, I minus 1 is 0, and then the delta x is a constant. We add them up, and we have our approximate area. Now, we know that it's not perfect because we can see for ourselves that, look at these gaps in here. We're understating the true area under this function. Here, it would have been the other way around if this was our function. So you're probably thinking, why are we doing this then if it's not correct? Well, you'll see very soon. Now, like I said before, we can also do right endpoint approximation. And now what's going to happen, as you can imagine, it's at the right endpoint, the height of the rectangle exactly touches the curve. So let's take a look. Right, okay, here we go. So if you notice the endpoints are on the right now, here we touch the curve exactly, and touch it exactly here and here. Those are the right endpoints. Now, by the way, if you notice, you know what? I just realized now, this L is supposed to stand for the sum of the rectangles when we're using the left point approximation technique. When we're using the right point endpoint approximation, we're going to call that sum Rn. So let's put them together so you can see them side by side. Okay, you can tell when it makes that noise, it's unhappy about something, meaning it's not cooperating. All right, I would like to copy this if it will let me. No, see, when it makes that noise, that usually means, no, I don't want to do that. Well, what I wanted you to notice is that with left, we start with f of x 0 and work our way up to x n minus 1. Actually, there might be another way to get around that. I have this program on here called Snagit. Which, by the way, used to come free with this package. Well, the only thing is it is grabbing all the handwriting, but still, at least we'll be able to see it. So sometimes you got to work around when the computer is being super stubborn. There can be ways of getting around it. So just as a point of reference, what I want you to notice, I'll highlight them in red. The beginning and the end of this approximation. So with the left, we start at 0, end up at n minus 1 because we're looking at the left endpoints. With the right, we're looking at the right endpoints, so we'll start at 1 and end up at n. That's the difference between the two. And if you notice in the formula, that's why it's written like that. Okay, so there's a sum of rectangles when we are using the left endpoint approximation, and there's going to be an approximation using the right endpoints. Now, are they equal to each other? That's a very good question. The answer is not necessarily. So now here's the steps that are needed to use this on an actual example. X squared over 2 over the interval. Now this is going to take a while, and you'll see it's like when we first learned about derivatives. Remember, we formally define them in terms of limits. And when you're asked to calculate derivatives based on the formal definition of with limits, you always probably notice that it took a lot longer than just using the rules. Well, something similar is happening here. This process is fairly time consuming compared to simply applying rules, but it's good to see how this works just once to understand what's going on behind the scenes. So you have something like this over the interval 0 to 3, which would be right here. So this is what you're trying to approximate. We're going to do it both ways, left and right endpoint. So let's just say that we decided that our interval should be 0.5. Delta x is 0.5. Let's see. Here we go. So these are the graphs. And so because we're going from 0 to 3. By one half at a time. So what are we going to do to obtain this result? So remember, from the left side, we're looking for the height of the curve at each of these left endpoints. The delta x's are simple. They're all equal to a half. We know that. So these are the left endpoints. Let me just put them up here one more time. So the left endpoints will be 0 up to 2.5, right? If you look at this graph. See, actually, I'll tell you what we're going to do here. Well, no, it's okay because this is the first interval, second, third, fourth, fifth, sixth. Okay. So the left endpoints will be the numbers 0 up to 2.5. Okay, within the last rectangle, this is the left endpoint, so we do not include the 3, right? So therefore, this formula, this is ln, by the way, the sum coming from the left endpoints is telling us to do this. So these are the heights, remember. This is the function evaluated at the left endpoint. Those are the heights. The delta x's are the width. They're all the same. So the function, remember, is x squared over 2. So look at how much work this is. I have to now go through here and substitute each of these left endpoints into the function x squared over 2. Now that's already been done here. It's 0, an eighth, a half, 5/8, 2, 3 and an eighth. Oh, sorry, 9/8, this one. And then the widths are still 0.5. So anyway, this ends up being 3.4375. That's the approximate area under this curve between 0 and 3. If we use the right endpoint approach, what will be different is that the right endpoints are going to be not 0 up to 2.5, but, well, 0.5 up to 3. And you can see they're here in the formula. We have to evaluate the function at these 6 points the, because that's going to give us the heights. Remember, the heights are coming from the right endpoint. Okay, like this one, for example. And the widths are still 0.5. So when you plug in these numbers, you'll see, oh, so they're not the same. And you can see from this graph, the one on the left is underestimating the area under that curve. The one on the right is overestimating it. So it makes sense that the right endpoint method is overstating the true area, and the left endpoint method is understating it by 0.6875 compared with 3.4375. So again, you're asking yourself, why do we bother with this technique? So we have to use our cleverness. What's going to happen is we're going to ask ourselves the following interesting question. What if I reduce delta x to not a half, but a quarter? I'll have twice as many rectangles, but each individual rectangle will slightly better fit that curve. Okay, so if we break this up into smaller and smaller rectangles, there'll be more and more of them that are exactly touching the curve and less area that's either too high or too low. So I don't know if I can actually draw that properly. Maybe I'll give it a shot. Let's see. What I could do is have a ridiculous example. We'll start with 2, and then we'll see how poor the approximation will be. Let's say that using the same setup, we had an interval from 0 to 3. Let's say I only have 2 rectangles. All right, let me draw this a little better. No, one more time. So here's the first rectangle. Now remember, this is the left endpoint. Oh my God. It's just, oh, okay, maybe this is not the best example. Yeah, that first one does have a height of 0, doesn't it? I didn't even notice that because that's the left endpoint. Oh, so that's really weird, but it's true. So that means this is our entire approximate area, and you can see it's not even close. But what if I had something like this? Even though this is a very crude set of drawings, it should be clear. I hope you can see that as delta x gets closer to 0, the approximation improves. All right, so I hope that diagram is making it clear that if instead of having 2 intervals, meaning delta x here is, let's say, a half. Let's say over here, delta x is something really small, like 20.25. You can see there's going to be a lot more rectangles, and there's going to be a lot more rectangles touching that curve. And so there's a lot less missing space, let's say. So you can see where this is going. These areas will provide the correct solution when we take the limits as delta x goes to 0. That's where this is going, okay? In other words, if I continuously shrink up the widths of these rectangles in the limit as delta x goes to 0, the area under the curve, no matter which approach I'm using, right or left, will give me the correct area under this curve. And that in turn is my integral. Okay, now we have this notion of Riemann sums, named obviously after Riemann, the great mathematician. Um, he he's famous for a lot of things that we take for granted. He's the one who came up with the idea of, he did a lot of work with imaginary numbers, among other things. Oh God, there's so much stuff here. I'm not sure. Yeah. Well, let's just say he was a heavyweight in this field. There's so much, so many things he was involved with. This is the 19th century, by the way. All right. Anyway, so Riemann sums are more general than what we just did, because here, if you notice, we were forced to choose either the left endpoint or the right endpoint. With the Riemann sums, we can actually choose other sections. We can choose the midpoint, for example, if we want to use that to calculate our area. So in other words, with the Riemann sums, we can literally have any point within each rectangle be used to represent or calculate the height of that rectangle. So within the interval, for example, xi minus 1, xi star is somewhere in the middle. It doesn't have to be in the actual center, by the way. So we could actually use this to define the height of our rectangle. So that's the point that must touch the curve. And of course, the formula is the same. We're going to add up all these rectangles. This is our delta x. And the height is going to be f of x I star. So we're going to do that for each of the rectangles, add them up, and that'll also give us an approximation to our area. But of course, if we take the limit as delta x goes to 0, we will come up with the correct area. Actually, this one is expressed in terms of not so much that, but as the number of rectangles is going to infinity. In other words, instead of calling it delta x going to 0, they're calling it the number of rectangles going to infinity, because it amounts to the same thing. Okay, so we can define our integrals in terms of these Riemann integrals, or Riemann sums, I should say, sorry, Riemann sums. And so this is the formal definition of our integral over the interval from a to b. Because remember, we only defined the areas within a given interval. And the same thing holds here. So if you go back to one of these graphs, the actual integral would be the true area under the curve between 0 and 3. And it can be defined in terms of Riemann sums. All right, so let's say we have x squared. This tells me that my interval is from 0 to 2. So this area is the answer to this integral. So what we're going to do is find it using the right endpoint approach, using that definition of the Riemann sum. Now, by the way, this is just the background. Once we start doing these real, you'll be able to use the definitions. The rules. It's important to know what the rules are where they're coming from, but I don't think you'll be asked to do any of these in the assignments. But anyway, so here's the interval 0 to 2. And sorry, delta x is going to be defined as b minus a over n, where those the a and b are the two endpoints. And so here it's 2 and 0. And so we choose the n, by the way. Okay, so if you want to have one rectangle, then n would be 1. If you want to have a million rectangles, n would be a million. So that implies that whatever are x0 within each interval, xi could be defined as, in this case, x1, as x0 plus 1 times delta x. Okay. So what it's just saying is that you can find any x by going to the starting point and add I delta x's to it, which in this particular example would be 0. We started at 0, and then we added I times 2 over n. And so for this specific case, xi can be calculated as 2I over n, where n is the number of rectangles that we chose. So now all of a sudden, now remember, we already introduced or reviewed the summation operators, and now it looks like it might just come in handy because the function is xi squared being evaluated over the interval from 0 to 2. So why don't we go back? Oh, by the way, now why is it written like this? Because we just got through saying that xi can be thought of as 2I over n. Okay, so that means xi squared must be 2I over n squared, which in turn is 4I squared over n squared. And now the Riemann sum will therefore be, here's our f of x, delta x is 2 over n. We already calculated that as well. So in other words, whatever the interval is 2, and we have 10 rectangles, then the widths will be 0.2. Okay. So this is our new Riemann. This is the way we will define the Riemann sum for this problem. Well, luckily, we are very skilled with the summation operator now. So first of all, algebraically rewrite this as 8I squared over n cubed. Now the n is a constant, by the way. That was determined inside the outside of the problem. We chose n depending on how accurate we need the results to be. So that's why n is out here. It is, in fact, a constant. The I is the index, so that has to stay inside here. And then, of course, we recall this formula that we like so much. And so this becomes 8 over n cubed times this formula. And then you could do the algebra, but that reduces to this. And so therefore, this integral can be written as the limit of this expression as n goes to infinity. Now, we've had some experience with this already, with infinite limits. Direct substitution here will lead us with when we have what's happening here is n is getting extremely large. It's converging to infinity, which means that ratio is going to 0. Same thing is true here. Now, if n was in the numerator, well, that would be a little different. We might have to end up using L'Hopital's rule, but here it's not necessary because we just end up with 0. So all of this simplifies down to 8/3. Now, once you learn the rules of differentiation, you can come back to this and double check this if you want, but it is in fact 8/3. Wow, that was intense. That was also was all the material for A. Now this chapter has 4 parts to it, by the way. I just want to point that out for A, B, C, and D. So why don't we see what's coming up in 4B? Let's see where it was. Just get a sneak preview. Okay, so what's going to happen here is we're going to continue to use this approach for a bit longer before we start to formally introduce the rules of integration. Still got a ways to go, but pretty soon we'll get to do some problems with with the rules. Yeah, there's still some theory coming up, including, ooh, this is a big result in calculus, the fundamental theorem of calculus. And what's great about this is that we don't need Riemann sums to get the results that we need. Because basically what you're doing is you're showing how integrals and derivatives are related to each other. And then we can go ahead and use the rules of integration. And then that's where we'll spend the rest of our time. All right, anyway, so I think that will be enough for now. I think we've had plenty of theory for one day. And so, like I said, the next time we get together, we'll be looking at 4B. We'll be continuing to dive more deeply into Riemann sums. And then eventually we'll confront the fundamental theorem of calculus, and we'll see how derivatives or differentiation is related to integration. All right. So I'll see you all next time.